Okay, so today Donovan and me is going to talk about graphene as a good material for future studies.
Kawun, can you turn and look at the audience when you say that?
Okay.
You're looking at the slides. Okay.
So basically what I'm going to cover is the motivation for doing this project and the physics behind this graphene studies and some of its properties. So this basically some search that we did from Google, showing the interesting applications to graphene. So basically, it's one of the most important carbon systems, and
this is where we actually will introduce the model.
Okay, hang on. Now, okay. When you say this, when you say mother of all carbon systems, it's a big deal, isn't it? Right? After you've shown all the links, the web links, the websites just now, you probably want to look at the audience and say that, as you can see, it is the mother of all carbon systems. You need to raise your voice a little bit for the impact.
Need some emphasis.
Correct. Yes. Otherwise, it all sounds the same. There's no sort of oomph. Carry on.
And there are many dimensions of carbon systems. For example, buckyballs and nanotubes and others. So it's basically a flat piece of flat system with carbon atoms.
So this is actually the part where we'll be using the models.
Okay.
So this is the energy function of graphene. So it's basically direct cones at the magnified portions. So basically this is the valence band and that one is a conduction band. So it shows an approximately zero band gap. So one side is having an electron spin of plus half and the other side is having an electron spin of negative half. So a typical conductor, semiconductor would have a certain band gap.
Okay, can I stop you there? After every slide you're saying so as a connector. Can you vary that a little bit? There must be other things that you want to use to join the ideas, am I right? Right? Things like, for example, as you can see, following from that, as a result, consequently, some kind of variation there.
Okay.
Alright, which is pertinent not randomly, but which links it better, rather than to say so all the time. Right? Carry on?
These are massless Dirac fermions which having a spin of plus half or minus half. As massless means without mass. So basically pseudo spin is a concept where they have spin but it's not like the type of spin that have angular momentum.
You really need to look at the audience more. Kawun,
Yeah.
because your face is glued to the PowerPoint slides. Okay? Carry on.
So massless Dirac fermions, the speed is relativistic. So it's 1 out of 300 times of speed of light. So basically, at this speed of light, the kinetic energy of the Schrodinger equation will basically fail. So we need to use a relativistic equation for this kind of systems. So Donovan's turn.
Counter intuition.
Alright.
How do you hand over to him? You finished the part on
But I
what?
just realized that it's not my part. No.
Yeah, okay. So you got to make the break very nicely.
Oh, I think
Professionally.
that, now I will pass over the time to
And
Dr.
don't pass over. That's a Jewish festival.
Handover.
Handover, yes. Okay.
Alright, thank you Carmen for explaining to us about some of the properties of graphene. So right now what I'm going to do is to introduce to you to two very counterintuitive phenomena that is seen in the graphene system. The first being the Klein paradox. So what exactly does the Klein paradox say? Let's just refer you to what you did last semester in atoms to molecules. Right? So we have a case here whereby we have the potential barrier, as you can see here. So back in atoms to molecules, you learned that with a barrier, okay, and when you have a particle incident on it, depending on the width and height of the barrier, you will notice that your transmission probability, basically the probability of a particle going across the barrier, should drop with increasing width and increasing height. Well, that makes sense, right? What does the Klein paradox say? The Klein's paradox, however, says the opposite. When the particle gets relativistic, as Carl talked about, relativistic matters Dirac fermions, okay, if the width of the barrier or the height of the barrier starts to increase, the probability of transmitting through the barrier actually increases. Very counterintuitive, isn't it? So, in short, two theories to explain this. The first has to do with the Dirac cone, which is over here. If you notice, you see red lines. So this actually confines your quasi-particle to only this particular portion, and so when it actually tries to get across, it cannot actually so-called change its spin, and because of that, the particle is actually forced to tunnel through the barrier. The other idea, which is even more interesting, is that when the relativistic particle is incident on the barrier, at this end, it actually spontaneously produces a particle and an antiparticle. Okay, the particle being the same as this fella, and then the antiparticle here will actually annihilate with this guy. So take it as this particle annihilates with the antiparticle here, disappearing, and on the other side of the barrier, this is appearing. Now, bad news is this. It is exciting, but this phenomenon is actually not really experimentally observed, and researchers are currently into trying to look at the graphene system to actually see whether you can actually observe some phenomena. An interesting consequence is this idea that you cannot actually suppress a particle into a location. Let's see why. So what we do here is that these are some calculations and simulations that we did, that some researchers did. We have an electron with a certain amount of energy, and we set two different barrier heights. One which is about 2.5 times the energy of the electron, and one which is about 3.5 times the energy of the electron. And we notice two curves, basically the red curve corresponding to this energy, and the blue curve. Interesting fact, look over here. What we do is that we actually have a two-dimensional barrier, as what Kawo was talking about, graphene in the mother of all carbon system, so you have a two-dimensional carbon system, and then you have a barrier like this. So when we fire electrons, we fire it at various angles from 0 degrees, basically normal, to around nearly 90 degrees, which is nearly parallel to this surface. And what do we observe? We observe that the tunneling varies quite wildly with angle. Sorry. And that over here, it is nearly 1. It is nearly perfect tunneling, which means you cannot even keep a quasi-particle in a box. Alright, I'll bring you through the second counterintuitive idea, which is called the anomalous quantum Hall effect. Hall effect, in short, basically refers to one applying a magnetic field magnetic field through a conductor which actually has moving charge carriers. And because of the interaction, you actually see a deflection. So that is, in very brief terms, the Hall effect. So what we tried to do was, in the quantum Hall effect, we actually tried to reduce the current to discrete levels, so you actually are supposed to observe this thing called discrete jumps. The results, however, were more surprising. So we noticed two graphs here. The first graph here corresponds to a typical two-dimensional semiconductor. Observe that you actually have jumps in both directions, yes, that is normal. And that you notice that there's an integer jump. This refers to the quantization of your charge that actually can travel in the quantum Hall effect. The thing is very surprising in graphene is that notice that for here, this is a 2D semiconductor, it starts at 0. But in the graphene system, no, not at all. Notice that at the 0 level, you don't actually have a plateau. And that is significant. And why is that so? You notice that you don't actually have integer jumps here anymore. What you have are half integers. And what could the reason be? You have your relativistic masses derived fermions coming in once again playing havoc. And that there's this idea of the Landau level. What is the Landau level? In a typical semiconductor, we have your energy levels, that you have energy levels occupying both the valence band and the conduction band. And these energy levels, when they're well defined, and then you don't actually have a zero energy level per se. So if you go back to the graph, you will notice that here in the semiconductor, well, you have no zero energy level, all you have are the blue energy levels and the yellow ones. But in the case of the graphene system, there is this zero Landau level here, and because of that, you actually have energy state there, so you're actually forced to jump at that point. Which means you have this half integer effect coming in. Well, this is just a short introduction to how interesting graphene can be. I guess this will actually pique your interest a bit more about the topic, and perhaps we'll see you again in the final presentation with more interesting information. Thank you for your time.
Okay, all right. You've got good, emphasis in your voice. Good sort of connection, rapport with the audience. You look at us when you speak. And the time that you spend looking at the PowerPoint slides and back again is good. Is as in like it's very brief, so you turn back and look at us. So overall, your presentation skills are quite good. All right. What you may want to do is for both of you, check the timing. Yeah. Right. See whether you can make it within the 10 minutes, because the way I see it, I think it's still going to be quite dicey.
I know, my side especially.
Of course, now I've been interjecting and giving you sort of comments and things like that. But even so, I think you need to check. Right? What do you think?
I guess maybe you spend quite a lot of time talking
Trying
about
to explain the
trying to
concepts,
explain
which
the
is why it's
concepts.
going to be time consuming.
So I guess rather than talk about it, maybe we can just put diagrams of it, kind of thing. Like for example, you had this polar plot of the transmission against incidence angles, right? So maybe you put so rather than spending time talking about you shoot electrons at different angles, maybe you just put one diagram of the thing.
The second.
Yeah.
Yeah, and also same for the Hall effect lah. Maybe we can put a diagram of this.
But you still need to refer to what's in the diagram, right? You still need to explain it, but maybe you can cut down on the explanation. Because don't forget, your audience here may not all be sort of, this is physics, am I right?
Yeah.
May not all be physics.
We actually assume they have certain prior knowledge because of a previous module that we have all done as a group.
Oh,
before,
everyone has done
called
that.
atoms to molecules.
Okay.
So there is some basis in which we can still refer to.
Okay, some common platform there. So like, especially the things that you're talking about, which he's mentioned, those they would have learned as well?
Not exactly. So we are trying to build from that platform onto more interesting phenomena.
Okay. So don't address the basics then, just go, just make reference to some of the basics and then build on it quickly. You can do that. Yeah. So Donovan, presentation skills, you're okay. Just build on that. Kawun, you need to work on it a little bit more, right? First and foremost, you need a little bit more eye contact, Kawun, with the audience. Is it because you don't know what you're saying yet? You don't know it well enough yet?
Yeah.
That you need to look at the slides more. Is it because of that?
I need to look at the slides and then think back.
Oh, okay. Do you think it's possible for you to like look and then turn back and then speak?
If it's possible, I don't want to look at the screen now.
Can you try one or two slides? I think the other group is not here yet, right?
They're coming in 10:15 or something like that.
Oh, that's fine. You guys have time?
Okay. I have lesson at
10 o'clock.
YH 10.
Oh, what is, it's 10 to 10, you need to go,
module or
right?
something like that.
Yeah, career mode.
Oh, okay.
One or two slides, a quick one.
Yeah, just do a quick one, just one slide maybe.
Okay, I just randomly pick one.
Yeah, his
After
part.
all, it's a big picture, right?
Yeah, try it. With more emphasis in your voice. Because you want to be persuasive, you want them to buy your idea.
Because it's a big picture, there's hardly any words, so yeah.
So basically, this energy function of graphene at various positions, at various axes. So the top one is a conduction band, the bottom one is a valence band. So basically, the electrons go from bottom to top to fill holes. Yeah. So basically, the diagonal line at the side refers to plus half spin or negative half spin. So basically, this is a magnified portion of the energy function with respect to space. Yeah.
Okay, better, but needs work, yes.
Actually, I was thinking when you say diagonal lines, right, I think the audience will be wondering where. So
It has got a laser pointer there, right?
Actually,
Yeah.
cue to the audience where.
Use the laser pointer.
Not that button, not that button. The one below.
Yes, use it. Alright, outline it to show.
Anyway, when you click once and you click twice, you notice I actually outline with words.
Okay. You need a little bit more practice. I'm here again on Friday afternoon.
Friday afternoon.
If you want to try it out, one more time. I'm also here for about an hour on Thursday morning.
Thursday
From 10
morning.
to 11. Because I have class after that from 12 to 4. So.
Thursday morning, unfortunately, that's my lecture slot.
Okay, alright. No, I'm saying specifically for Kawun actually.
Oh.
Yeah, unless you both want to go through,
Actually, on Thursday morning, we are actually trying to rehearse with a group in the life sciences so that we
Okay.
actually see whether they understand our presentation.
Yes, and also you need to prepare for questions.
Question.
Yes, there will be questions, believe me.
And questions are targeted.
Very, very pertinent.
Sometimes they target the presenters.
Yes, there will be questions. I mean, from my experience in going 2 rounds with this, they will ask you very, very pointed questions. So you need to prepare. Right? Okay? Right. Do you have any questions?
No.
No? Maybe know your presentation a little bit better and then rehearse on your own, practice a little bit on your own with the screen, Go through the slides and then practice saying it. You need to have a little bit more emphasis in your voice, more eye contact, gestures. I know whatever comes naturally to you. Of course, overnight you can't become like a, Anthony Robbins or whatever it is, but whatever comes naturally to you.
Here's a problem already. I noticed that the contrast is actually not very good. You notice? I actually can't see the answers.
Yeah, yeah.
I need to go and do something about this
It's
picture.
very light. You are the one mentoring them for
Yes, the technical content.
this proposal.
Yeah.
It should still be visible, right? The red and green.
I think
Because I'm trying to
the
hide
green can see red also can see
the green part.
Green I think should be okay.
But I'm trying to highlight 2 different parts. I need to go do something about that too.
How many slides do you have?
16.
Hmm.
That requires work, right?
Yeah. For 10 minutes.
I think I go first.
Yeah, you better go. Okay. Bye. See
I
you.
was shocked at first also because initially we thought it was 15 minutes. Until
But
they
it's
sent us an
15
email,
minutes.
oh, every group will have 15 minutes, 10 minutes of presentation and 5 minutes of Q&A. They're like, what?
Have they shortened it this time?
That's for the next
Was it
semester.
like 15 plus 5 before?
Final is 15 plus 10.
Oh.
Half an hour, actually, if I'm not wrong, from what I remember from the briefing.
Mm.
At least Congress follows like this format.
Mm. Yeah. So you get 20 minutes, do you? No, 25.
15, 10, that's for the final. For the
15 plus 10 is 25, right? Yeah. And then 5 minutes is like changeover time, I think.
which I will need to make full use of because I'm actually using my Mac.
How many groups are there altogether?
14.
14 groups. Oh, it's about the same. 7 before and then 7 after.
The songs are okay, right? Besides what I noticed just now about the unusually light axes and things like that. The slides are okay, right?
The slides are okay except for that one where you were... I couldn't see the numbers.
Which one?
You know the ones at the side there are numbers, they're very faint. Further up, I think it's further up there. It's that graph, yes. Can you see? Are those numbers? There's something there, right?
Yeah, these are numbers.
Isn't it very light?
Yes.
It's very light, you know.
Okay, I will manually draw in my own lines.
I guess maybe the numbers don't really matter that much.
The numbers don't
don't
matter,
matter.
the axes
The axis
matter.
matters, yeah.
Okay.
I'm going to do something about this. I realized it only now because when I go through we're presenting, it's like, okay, everything seems okay. Then I made the audience, hey, dude, this doesn't look right anymore. Oh, this is still recording. Oh, dear.
Still recording.